All right, so today we'll continue our chapter 2.1, and let's start with the homework problems from last class. All right, so the average rate of change for this function as x changes from a to a plus 2 is 13. Find constant a. So what we need to do is find the slope of the secant line, so just the change in y over change in x. So the change in x is simply a plus 2 minus a. So that's going to be on the denominator. And then the change in y is going to be f of a plus 2 minus f of a. And a really easy way to calculate that is to consider it term by term, right? So what we're really doing here is 2a plus 2 squared plus a plus 2. Subtract 2a squared plus a. So what I like to do is I would like to group it by these terms, right? So I want to group it by 2x squared and x squared. So what I'm going to do is I'm going to do 2 times, and it's going to be a plus 2 squared minus a squared, and then plus a plus 2 minus a. What that really helps is that helps to simplify the expression and avoid errors. So a plus 2 squared is a squared plus 4a plus 4, and subtract a squared, that's going to be 4a plus 4, so that's going to be 8a plus 8, and then a plus 2 minus a is going to be 2. So plus 2 divided by 2, and that's going to give you 4a plus 5, which has to equal 13. Therefore, a equals 2, and that is your answer. So organizing these by the powers is a really useful method that will become handy later on when we get to integration. So just take note of that. Okay, so number 3, the average rate of change for the function as x changes from 1 to 3 is equal to the differential coefficient at x equals c, where c is between 0 and 3, right? We always have to pick up on these subtle restrictions here. So what we're going to do is pretty simple, right? Find the average rate of change. So that's 3 minus 1. F of 3 is 9 minus 9 equals 0, and f of 1 is negative 2. So negative 2 is 2, and that has to equal f prime of c, right? So we can calculate f prime of x. So remember, power goes down and it decreases by 1. Same thing here. So f prime of x is 2x minus 3, and f prime of c is going to be 2c minus 3. So 2 over 2 is 1, so that has to equal 1. All right, so c has to equal 2. All right, so that was a pretty easy problem. Okay, so if you have learned pre-calculus 12, then you can look at this a little bit more challenging problem. All right, so differentiable function f of x satisfies f of a minus f of b over a minus b. Now, you should immediately think of, when you see this, the average rate of change between x equals a and x equals b, right? So recognizing those forms and patterns are very important. And that always has to be greater than f prime of a. Geometrically speaking, that's the slope of the tangent line at x equals a. For real numbers a and b where a is less than b, which of the following is a possibility for the equation of f of x? So option A here is y equals log of x. So if you draw that out, it's going to look like this, right? It has an x-intercept of 1, and it's a curve that's shaped like that. Now, we have to make sure that for any real numbers a and b where a is less than b, so maybe a is here and b is here, the slope of the secant line between a and b has to be always greater than the slope of the tangent line. And as you can see with just the example that I've drawn here, that does not hold true, right? So if we set a here and b here, we can see that the slope of the tangent line is about, is about like that, roughly. And the slope of the secant line is like that. So it's less than the slope of the tangent line. So log of x cannot be an option for our conditions. All right, so the next curve is x squared minus 1. So that everyone should know how to draw, right? All right, so x squared minus 1 is a parabola that roughly looks like this, something like that. And we have to either provide a counterexample or prove that this is true for all possible a and b. So now if we, you can trace along the paper with your pencil while you're doing this, maybe. If this is a and if this is b, right, we just choose any a and b. You can see this is the slope of the secant line, and this is the slope of the tangent line. Now, the slope of the tangent line must always equal less than the secant line, but this is true because the slope is negative, right? If this is like -3, then the slope of the secant line will be something like -2. So it holds true when we select A and B here. Is there any place where this is not true? And try a couple of different values of A and B to verify that. Here, the slope of the secant line is positive while the tangent line is still negative. So that's completely satisfying the condition, right? And even if we pick both of them to the right side, look what happens, right? This is the slope of the secant line, and the slope of the tangent line will always lag behind the secant line because the curve goes up, right? It increases. So for now, this seems to be holding true for all possible values of A and B, right? We've covered where A and B are on the left-hand side, one is on the left hand and one is on the right hand, and if both of them are on the right-hand side, right? So it holds true for all three of those cases. So B is likely our correct answer. But let's move on to the other graphs. Sine x. So sine x is a trig function which has period 2 pi, and it looks like this, right? Roughly, my drawing skills aren't that great on the iPad, but it roughly looks like that. So let's see here. When we looked at the log graph, notice how if a curve is sloping upward like this, then it doesn't hold true, right? So we can immediately apply that to our trig graph. Let's see if I can draw a better upward curve. So it kind of looks like that. All right, so when we pick A and B on the 2 points that have the upward curve right here, you can see that the slope of the tangent line is going to be greater than the slope of the secant line. So immediately that's a no for us, right? So it has the same upward portion as the log graph. And our final option is negative x squared plus 1. So it's an inverted parabola from option number B. So this is option D, negative x squared plus 1. And let's see here. So if we pick, let's say, if A is here and B is like here, then this will be the slope of our secant line, and this will be the slope of our tangent line. Again, the tangent line has a greater slope than the secant line, so the curve is automatically out. So if we chose A here and B here, and found that it violates our condition. So only option B would make sense as our answer, right? So just comparing the geometric values of the slope of the secant line and tangent line will get you through this problem. All right, so, number 7 was a pretty important one in my opinion. It tests on how well are you able to manipulate the expression so that you can use the definition of the differential coefficient, right? So number A, okay, so we're given that f prime of 2 equals 12, and that's pretty much the only function given other than it's a polynomial, so it's all smooth and differentiable. Which of the following values is the largest? Now, remember last time I told you to memorize, memorize and understand, right? 2 different forms that you can take with the definition of the tangent line. One form is f prime of A can equal either x goes to A of f of x minus f of a over x minus a, or that h goes to 0 of f of x plus h minus f of x over h, right? These are the 2 most common forms. But in the end, I told you that whatever goes inside these brackets, as long as that they are matched in the denominator, it becomes a f of large A minus large B scenario, right? Oops. So if this is large A and large B, as long as the denominator follows large A minus large B, then this becomes the definition of the slope of the tangent line because it represents that 2 points are getting infinitely closer and closer together. So with that in mind, let's look at option A. Now, it looks very similar to the definition, except that it's a 0 over 0 limit, first of all, when you plug it in. But the numerator has x minus 2, right? So the denominator we would also expect, we would want to have x minus 2 in order to use the definition here. But you can see that it's x squared minus 4, and then it becomes quite obvious that you need to factor the denominator, right? So noticing that we want an x minus 2, and we can easily obtain an x minus 2 by factoring the denominator. So let me group it like so. And then here it's going to be multiplied by 1 over x plus 2 from the factoring. Now we can remove any constant that converges to a non-zero number when we're taking limits. Remember, anything that converges to something that isn't 0 can be taken out. So this converges to 1/4. So we can take that out, and immediately you can recognize that this expression is the definition of f prime of 2. So f prime of 2, which must equal 4 times 1/4 times 12, which equals 3. So that's the value for A. So B, we have f2 plus delta x minus f2 over delta x. So remember that 2 plus delta x minus 2 is simply delta x, and this exactly is the definition written here, right? So this is literally going to be just 12 without any modifications. Okay, so for option C, we can see that we have f of 2 minus 3h, but we have 2h in the denominator. So what do we want our denominator to be? We simply take, right, a minus b. 2 minus 3h minus 2 equals negative 3h, and that's what we want in the denominator. So what I'm going to do is I'm going to start by writing that out. So limit as h goes to 0 of f of 2 minus 3h minus f of 2. But in the denominator, we're going to write it as if it's negative 3h. We want that result, right? This would be the definition of f prime of 2. But originally, we had 2h, so we are going to have to cancel out the 3 in the numerator and multiply the original 2 in the denominator. So this is going to be f prime of 2 times negative 3 over 2. So that's going to be negative 18. Okay. Now D, it looks more complicated, but remember the underlying thing that we want is the same, right? We want to compare the change in the input of the function. So 2 minus 3h minus 2 plus 2h, don't forget the bracket, is going to be negative 5h, right? So we want negative 5h in the denominator. So I'm going to write it like that, and then we can change the coefficients later on. So I'm going to write negative 5h, and the numerator is going to be f of 2 minus 3h minus f of 2 plus 2h. And then we need a cancellation of that, and originally we wanted 6, so negative 5 over 6 would be multiplied. And if we plug in f prime of 2 equals 12, that would be 2 times negative 5, which is negative 10. Okay, so the final option here is 2h plus 2, and then we want to subtract that by negative 2h plus 2, right? So that's going to be 4h. So we want 4h in the denominator. Oh, did I write the wrong options? Yeah, so B was pretty easy. So this was C, this was D, and this is now E. We want 4h as h goes to 0 of f of 2h plus 2 minus negative 2h plus 2 multiplied by, we need to get rid of the 4 and replace it with a 3. So it's going to be 12 times 4 over 3, which would be 16. So this final option equals 16. Now it tells us to select the largest value, which would be option E. Okay, so by looking over this problem, you should be comfortable with manipulating and changing these expressions so we can use what we've got, which is the definition of f prime of 2. All right, so that was pretty important. Okay, now we solved all those challenging ones. This should seem pretty easy, right? All right, so we're given f of 3 equals 4 and f prime of 3 equals 24, find this limit. Now, if we plug it in, it's a 0 over 0. Oh, no, it is not immediately clear that it's 0 over 0. Oh, but f of 3 equals 4. Yeah. All right, so it is pretty observable that it's 0 over 0. So we need to modify this expression, which is the important part. Now, I think I said last time that if we see that f of 3 equals 4 and you see it in the limit, it's better to replace that with f of 3, right? So let's go ahead and do that. But there's one slightly annoying thing, is that the limit isn't going to 0 necessarily. And we have x plus 1 here in the numerator, right? So if you can see the picture immediately, you don't need to substitute. But if you don't see the connection to the derivative immediately, here's what I like to do, right? So we talked a lot about substituting. So what I'm going to do is I'm going to make this go to 0. In order to make this go to 0, I need to substitute, if x goes to 2, then x minus 2 would go to 0, right? So I'm going to substitute t equals x minus 2, and then the limit can be rewritten as limit t goes to 0 of, let's see here, x minus 2 squared minus 4. So that's going to be x squared minus 4x plus 4 minus 4. So that's going to be x squared plus x squared minus 4x, right? Yeah, x squared minus 4x minus 4. So it's going to be x squared minus 4x in the denominator. And here it's going to be f of oh wait, sorry, I messed this up. Right. So if we want to substitute, we want to make sure we express x in terms of t. So x equals, so if we did this, we need to say x equals t plus 2, and then we need to replace that, right? So it's t squared plus 4t plus 4 minus 4. So it's t squared plus 4t. And then here we have t plus 2 plus 1, which is f of t plus 3 minus f of 3. Okay, so now what we got is we got a limit going to 0, right? What we want to do is we want to look at the numerator. So f of, we can rewrite this as 3 plus t. That looks like f of 3 plus h minus f of 3, right? So we want to use the definition of f prime of 3. Limit t goes to 0 of f of 3 plus t minus f of 3 over, we want t, right? We want t in the denominator, but notice how this factors to t times t plus 4. So this t plus 4 is left over. And as t goes to 0, we can pull that out as 1/4. So it's 1/4 times f prime of 3, right? So that's going to be 1/4 times 24, which is 6. So that would be your final answer. Okay, so if the limit is going to some other number that's pretty difficult to interpret, the best bet you have is substituting and then representing the limit in terms of that substituted variable. All right, so let's go to number 10. All right. Differentiable function f of x satisfies f of x plus y equals f of x plus f of y for all real numbers x and y. Given that f prime of 7 equals 3, find f prime of 0. Now, this is what we call a functional equation, okay? A functional equation is when you're given some properties related to a function. Here it's f of x, and this is a given property of that function, and you're trying to find what that function is. Now, that's when you're solving an actual equation, find this function that satisfies this. But what we're trying to find is f prime of 0, and it's really interesting that they ask us to find the differential coefficient rather than the function itself, right? So we need to look at what this is, and then we need to try to get a definition of the derivative out of it. As you can see, we have two variables here. So we have x and y. So let's see if we can do anything about that. So remember that the definition of the derivative is f of x plus h minus f of x. And if we let the variable y act as h, then we can slightly rearrange it so that f of x plus y minus f of x equals f of y. And what we need to do is, in order to finish that definition, we need to first of all divide this by y. So let's do that on both sides. And then we need to take the limit y goes to 0. And then on the left-hand side and the right-hand side as well, y goes to 0. And on the left-hand side, what you will have left is this will become f prime of x. And on the right-hand side, this will be limit f of y over y, right? So remember that when you plug in 0, the denominator goes to 0. The limit must exist because it's differentiable, right? So you have to pick up on these subtle conditions that are given to you. You're guaranteed that the limit exists because it is differentiable, right? So 0 and the numerator goes to 0. So this is technically saying that y minus 0 over f of y minus f of 0, because the numerator has to go to 0 as well. So this will be the definition of f prime of 0. So on the right-hand side, this is going to be f prime of 0. And remember, f prime of 0 is just a number, right? You plugged in a specific value into the derivative. But on the left-hand side is the definition of the derivative itself. So it turns out the derivative is actually a constant number. The derivative is a constant such that when we plug in x equals 7, f prime of 7 will also equal f prime of 0. And we're given that that is equal to 3. So our final answer is 3. So manipulating this expression, this functional equation, into the definition of the derivative to use the given condition is, I think, quite an advanced skill here. All right, so 11, I think I told you that we can go over this together in class. All right, so let's prove the following statement that if the function is differentiable at x equals a, then the function is continuous at x equals a. Okay, so we're given that the function is differentiable and we want to prove that it's continuous. Remember, in the end, we want something like the limit, right, of x goes to a of f of x equals f of a. So that's the definition of continuity, right? So what we can do is, because f of x and f of a, you remember the other definition, f of x minus f of a over x minus a, that was the definition of the differential coefficient, so the slope of the tangent line, right? So maybe what we want to do is we want to take the limit of x goes to a of f of x minus f of a. And what we can do is we can start with this limit, but we can immediately modify it so that it becomes the definition of the slope of the tangent line at x equals a. We can divide this by x minus a, and then multiply it by x minus a, right? And then we can say that, hey, this is going to equal f prime of a, right? So this is f prime of a, and multiplied by, this is going to 0, right? We're assuming that f of x is differentiable, so this won't be infinity and that make like a weird indeterminate, right? So we can pull out the 0 in this case because it is not indeterminate. F prime of a times 0, which equals, right, because this 0 is multiplied by a constant number, which is not infinity, then we get 0 as our limit. And remember, we can split these apart because f of a was just a constant, right? So limit x goes to a of f of x minus f of a. So here the limit only applies to f of x here, equals 0. So therefore, limit x goes to a of f of x equals f of a, and that is the very definition of continuity that we want. So that proves that if it's differentiable, then it's continuous. But remember, proofs are only one way, right? So if we proved this, it doesn't automatically imply that the opposite statement is true, as we've shown in the notes. All right, so number 12. How many points are there in this interval, -1 to 4? So it's greater than -1 and less than 4. f of x is not differentiable, right? So number one, we should remember that if it's not continuous, it cannot be differentiable at all, because differentiability automatically means continuity. Did I introduce you guys to the contrapositive statement? Maybe not. So in logic, there are a couple of different types of statements here. If I say if A then B, right? The double arrow, I think I said that, means that this is known to be true. If this is known to be true, then there is only one option where we can say that it's definitely true, right? So we can say that if statement A, if A is B, and we know that to be true, then we can say for sure that the negation of B, so not B, is not A, right? This is called the contrapositive. Okay, so there's three types of statements, right? So the original statement is called conditional. The inverse is B goes to A. So you're just swapping B and A. The converse, oh, sorry, I messed that up. The inverse is not A is not B. The converse is B is A, right? So this is inverse, converse, yeah. And the contrapositive is not B goes to not A. So you flip them and you also put a not in front of them. The only statement that is guaranteed to be true if the original statement is true is only the contrapositive statement. So if I say that a function is differentiable at A, then it's going to be continuous at x equals A. Then what must be true always is we put a not in front of this, and then we send that over, not in front of this, and we send that over. If it's not continuous, then it has to be not differentiable, okay? So if it's not continuous, oh, here we go. As you can see, this is not continuous, and this is not continuous, right? So we automatically found 2 points where it's not going to be differentiable. And we can see the other point here. It's a sharp point, so the left-hand limit of the differential coefficient and the right-hand limit will not match. So in addition, there are a total of 3 points where this is not differentiable, okay? So step number one would be looking for discontinuous points. Step number two would be looking for continuous but not differentiable, so these sharp points. Okay. Number 14, if f of x is laid out like this, then find the value of f prime 1. So here we can take the derivative, right? F prime of 1 equals, remember that the power goes down and it subtracts by 1. So the 2 goes down, but it multiplies with the 1/2 to form 1. So it's just going to be x. And the same thing, the 4 goes down, but it multiplies with 1/4. So it's going to be x cubed plus x to the 5 plus all the way to x to the power of 99, right? So f prime, well, I should say f prime of x, right? Not f prime of 1. F prime of 1 would be plugging in 1 to all of these. There are how many odd numbers? These are 50 odd numbers, right? So f prime 1 would be adding 1 50 times. So that answer would simply be 50. All right, so if f of x equals 7x cubed minus ax plus 3 and f prime 1 equals 2, find constant a. So we just take the derivative, right? The derivative of f of x is the power goes down and it subtracts by 1. So 7 times 3 equals 21, x cubed minus a, and then the derivative of a constant is 0, so that's gone, right? So f prime of 1 equals 21 minus a equals 2, so a has to equal 19, and that was a pretty simple question as well. So, and that was the end of the homework, I think. Number 16, we proved that in the previous lesson, so you can rewatch that if you want to go over the proof of the product rule again. All right, so let's go over this again. All right, so we left off with the product rule last time, right? So if we wanted to differentiate a function where two functions are multiplying, we simply go and take the derivative of the first one, leave the second one alone, leave the first one alone, then take the derivative of the second one. And I left you with a little special case where if it's f of x squared, then it's going to be these two identical terms, which leads to 2f of x, f prime of x. And there are some applications in polynomial division if we're dividing by something squared. Because in the end, in order to find a remainder, if a remainder exists, you need two separate equations, right? Normally, for if you're dividing by a quadratic expression, your remainder will be linear. It will be ax plus b. And you need two equations to solve for those two variables. But sometimes if it's squared like this, you can only deal with one. And that's pretty difficult, right? So what you can do is you can take the derivative and then plug in 0 again to cancel out all of these terms. And hopefully find another equation that you can use for your remainder. If it's divisible, then you can get the fact that both f of a, then f prime of a will also be 0. But that's a pretty special case dealing with polynomial division, and you'll see one question about this. But today I want to introduce you to the chain rule. Now the chain rule is, there's multiple layers to it. In this course, I'll introduce you to the first layer, which is the derivative of a composite function, right? So we touched on this just a little bit here. So this is technically what? A composite function, right? So you're taking a function and then you're putting it inside another function, which is x squared. So it goes from x to f of x squared, right? So, and then we were able to get away with the product rule for this one. But what if the expression was like more complicated, like 3x minus 2 to the power of 7, right? We definitely wouldn't want to be expanding all that. We also probably won't want to use the product rule because there's like so many terms multiplying with each other. So what we can do is we can use something called the chain rule. Now, given that two functions f of x and g of x are differentiable, the derivative of the composite function y equals f of g of x is f prime of g of x times g prime of x. Now this part will probably not be too surprising for you, right? So what we want to do is treat this as a single object and then just take the derivative as we normally would. What might surprise some of you is the additional multiplication by the derivative of the inner function we have here. So what we need to do for this one, if we're using the chain rule, is we would treat the inside function, right, the inner function, 3x minus 2, as a single thing, right? Like sort of treat it as a single variable and just take the derivative as we would normally do. So the power goes down and it subtracts by 1. But we also have to multiply that by the derivative of the inner function, in this case is 3, right? So we would get 21 times 3x minus 2 to the power of 6 as our answer. And if we go back up here, you can see that the chain rule is directly applied, right? If we differentiate f of x squared, then it's going to be 2f of x, right? We treat f of x as a single object, but you can also see that it's multiplied by this f prime of x term. So where does this inner function derivative come from, right? So I'm going to give you a quick and easy proof of the chain rule. So always when we try to find the derivative of a function, we have to start with the definition of the derivative. So the definition of f, let's call this y prime. Y prime is going to be limit as h goes to 0 of, we want to first plug in g of x plus h, right? And then we plug in x, and then here we write h, right? So this is the definition of the derivative. Now notice in all the limit problems that we've been doing, we need to match the denominator with whatever is being put into the larger function here, right? So if we look at the outer function, the thing that's going into these outer function is g of x plus h and g of x. So that should be matched in the denominator. So what should be in the denominator if we want to make an expression for f prime of x is this, right? We should have this in the denominator. So let's rewrite and modify the expression so that we do have that in the denominator. Minus g of x, and then here in the numerator, it's going to be f of g x plus h minus f of g of x. And then since we multiplied this in the denominator, we need to multiply it again in the numerator to cancel this out. And the original thing that was there was h, right? And here we can see that when x goes to 0, when h goes to 0, sorry, this goes to 0 and this goes to 0, but specifically the input of the outer function goes to g of x, because when h goes to 0, then the input gets closer and closer to g of x. So that's going to be the input of the outer function. So we get f prime, but the input of that is going to be g of x. And then here on the second term, this is the very definition of the derivative for g prime of x. And there we go. So that's the chain rule and how we calculate it. That means that we always have to remember to multiply the derivative of the inner function when we're differentiating composite functions. So just correctly identifying the outer and inner function and just remembering to keep the g prime term multiplied is the spirit of the chain rule. Now the chain rule, it's very important to understand how composite function works. I think I drilled that into you enough already, because when you go to a full calculus class, the chain rule is going to be the basis for all sorts of more advanced techniques that you're going to learn, both in differentiation and in integration, which is the next unit. So having a good understanding of the chain rule is really essential for your success in calculus. And of course, this goes far more deeper in the full calculus course, but we'll leave it here as a technique to differentiate composite functions for now. And this is the final notes, which was finding f prime given a functional equation, was what we just did in question number 10. Plug in x equals y0 to obtain f of 0. If you require additional information, then this is a good place to start. Plugging in easy numbers or getting all zeros will definitely help. And modify the expression so you get the definition of the derivative was how you tackle those challenging problems. All right, so let's go back to the notebook, workbook, and let's see here. Number 17, if you looked at this and just went straight into the product rule, you can do that, or recognize that this is actually just x to the 4 minus 1. That might have saved you a lot of time. So remember that x to the n minus 1 equals x minus 1 times x to the power of n minus 1, n minus 2, all the way to 1. And this is for all natural numbers n. And x to the n minus 1, n plus 1, sorry, can be factored into x plus 1. And then we have x to the n minus 1, but we switch signs. Plus x to the n minus 3 minus all the way to 1 if n is odd only. Right, so x cubed plus 1 can factor into x plus 1, x squared minus x plus 1, right? I think we're all familiar with that. The final sign then will be of plus because n is odd, but this only works for odd exponents. So these are some factoring rules that you might want to keep in mind. All right, so number 18, this is just a product rule exercise, so I'll leave that up to you for homework, so you get comfortable with using the product rule. Number 19, quadratic and polynomial, the slope of the tangent line. This is also just utilizing the product rule, right? So this is basically just put the product rule in context and you should be good. All right, so number 20, polynomial function f of x satisfies this. So let's just walk over this together. X goes to 2, x minus 2, f of x minus 3 goes to 4. Again, the limit must exist, but the denominator goes to 0. Therefore, the numerator must go to 0 to make that indeterminate form. So f of 2 has to equal 3. Now we have to go back to the limit and say that, hey, since we figured that out, we're going to replace 3 with minus f of 2, and then we can immediately see very clearly that this is going to be f prime of 2, and that's going to equal 4, right? So always go back to the limit and figure out that additional piece of information. Find g prime of 2. Let's use the product rule. So what the two functions that we have multiplying is x squared and f of x, right? So we're going to take the derivative of the first one and leave the other one alone, plus we leave the first one alone and take the derivative of the second one. So that's going to be your g prime of x, and g prime of 2 is simply going to be 4 times f of 2 plus 4 times f prime of 2. And we got f of 2 equals 3 and f prime of 2 equals 4. So that's going to be 4 times 7, which equals 28. Okay, so getting the information from the limit and plugging in using the product rule, not too difficult, I think. Right, number 21. We're going to solve this together, but I encourage you to pause for a while and try to get a solution here. So, okay, I'm assuming that you thought about this for a while. What you can do is, since these are both going to 0 over 0, you can factor it, but it's not a very pretty polynomial to factor, right? You can use synthetic division, but it's x to the power of 9. So it's kind of, you have to write 9 coefficients and then do synthetic division. Maybe there's a simpler way to this. And if you look hard enough, there is. If you notice the coefficients, when you add these coefficients, right, 1 minus 5 plus 10, it's going to be 6. And it's no coincidence that this is 6 and what you're plugging in is 1, right? So if you treat this expression as your f of x, okay? So if you set this as f of x, then what you have here is limit x goes to 1 of f of x minus, since we know that f of 1 equals 6, right? F of 1 is just the sum of all the coefficients, right? Over x minus 1. And suddenly this gets very simple, because this is the literal definition of f prime of 1. And f prime of x, we can do that quite easily, right? 9x to the power of 8 minus 15, x squared plus 10. And we can just, plug that in. 9 plus 10 minus 15 equals 4. And that's our answer, right? So it's worthwhile to take just a couple, maybe once you get more familiar with it, a couple seconds observing your expression might lead you to some simpler calculations than dividing the entire thing from the get-go. All right, so that was number 21. Number 22, I think, combines all the skills that we did, right? So combining the modifying limits expressions and finding the values of some unknowns. So I'll leave that for homework for you to practice. And number 23, I think this was in the notes as well, right? So initially this looks like an infinity times, if we plug in infinity, that's going to go to 0. So it's an infinity times 0 limit. And we have to modify this limit in some way, right? So I think this was in the notes. If we substitute t equals 1 over x, right? Then this expression becomes, as x goes to infinity, t goes to 0, and x is 1 over t, right? So this becomes 1 over t, and this becomes 2 plus t and minus f of 2. It was just the differential coefficient at 2 hiding in disguise, right? You just flipped everything. So this is just f of 2, and taking the derivative of f of x, that's just another product rule exercise, right? So take the derivative of the first one, that's just 1, multiply it by the second one, plus take the derivative of the second one, and then leave the first one alone, like that. And f prime of 2, you can just plug it in, right? There's really no need to simplify it if you're not if you're just going to plug in a number. 9 plus 3 times 4. So that's 12 plus 9, 21. And that would be your answer, right? So that's f prime of 2. Cool. So that's easy, well, and done. Number 24. Okay. I think this is pretty straightforward enough, so I'll leave that as homework, right? If you have two unknowns, you should get two equations, and looking at this limit, you should be able to get two pieces of information out of it, right? Okay. Number 25. Quadratic function f of x satisfies f of 0 equals 2, and this equals 2 for all real numbers x. Okay, so whenever you see for all real numbers x, you've stumbled upon an identity, right? An identity is an equation that holds true for all possible values of x, right? When we first learned an equation, we defined it as an expression that is sometimes true and sometimes false depending on the value of x, but it says that, hey, this is true for all values of x. Then you can do a lot more with it. Usually in calculus, what we can do is whenever we encounter an identity, should we plug in values? Should we differentiate both sides? Or should we integrate both sides? And that's coming up in the next unit, so let's not worry about that for now. But those are some things that you can do. You can perform the same operation on both sides and it will still hold true for all real numbers x, because that's what identities are, right? So we're given a additional condition about our quadratic function. So this itself narrows us down to two variables. And using this, I think we can manage two variables. So with this, I'm going to set myself up as ax squared plus bx plus 2, because that's the y-intercept, right? So what I can do here is, can I plug in some easy values? And turns out yes, right? Because x minus 1 is multiplying this f prime of x term. And if we plug in x equals 1, then that term will go away. So 2f of 1 equals 2. F of 1 equals 1. So f of 1 is a plus b plus 2. A plus b plus 2 equals 1. So a plus b equals negative 1. So we got one of our equations here. And what else? We can also try if a plus b equals negative 1, then we can try f of 1, right? Because if we plug in 1, that will automatically give us the sum of the coefficients a plus b, right? And we know that it's negative 1. So let's oh, sorry, we already did that. Never mind, my bad. So what we can also do is, what's some easy values that we can plug in? We can plug in 0, right? That will give us the constant 2. And I don't think that's too bad of an idea. Right, so let's plug in 0. So this was x equals 1 and x equals 0. 2f of 0 minus 1, so that's plus f prime of 0 equals 2. F prime of 0 equals, so f of 0 equals 2, so 2 times 2 is 4. And f prime of 0 should equal negative 2. And at this point, we can take the derivative of f, which is f prime of x equals 2ax, right, plus b. And that gives us f prime of 0 equals b equals negative 2. All right, so now we got b equals negative 2. So from this equation, we can get a equals negative 1 minus b, which equals 1. All right, so therefore our f of 2, which is the final thing that we're supposed to find, equals 4a plus b, which is 4 minus 2 equals 2. All right, so that would be our final answer. All right, so I think as long as you found some nice values to plug in and set up the equation properly, right, it's not too complex to solve these types of problems. Number 26, I'll leave this as homework. So this was the question that I was talking about. Usually when you divide, right, when you divide something by a quadratic, your remainder should be linear, right? So you'll get two unknowns as your remainder. But notice that there's only one good value to plug in, and that's -1, since that will cancel out the quotient term, right? Unless you want to, really want to do polynomial division, which is, if you want to solve this quickly, then you probably shouldn't go down that path. But how can we find that other equation that makes us complete a system of equations about A and B, right? So we need two equations. We can get one from plugging in -1, but the other one we would need to differentiate both sides and then plug in -1. So I would use that approach for solving number 26. All right, so that's the end of our chapter here. So yeah, so here were the proofs for the binomial theorem and the product rule. So the homework would be finishing the rest of 2.1, and next time we'll really get into what we can do with the derivative, right? So up until now, we've mostly focused on the algebraic part, manipulating expressions. There were a little bit of interpreting the geometry of it, which we'll get way more into in more detail. But next time, we're going to see what we can actually analyze and what types of problems we can solve by using the derivative, okay? So thank you for watching, and I'll see you in the next chapter. Bye.